take that one out. Maria, I'll get you a copy of it when we have a minute. So I want to quickly go over this so that you have your answers. So it asks you at which value is there a relative maximum? And we get a maximum. And one of the most important things that we talk about while we're looking at this kind of stuff is what graph are we looking at? What graph are we looking at? The graph of what? Yeah, this is the derivative graph. So when you want to know if you're quickly reading this test question and you're like not paying careful attention to what's going on, you might think, oh, this is like algebra 2. Here's my max. I see it. It's the biggest one on. Okay, is it? No, it's not, because since it's the graph of the derivative, I know that my critical points are where my derivatives are equal to 0. So now the conversation comes, which one of these is a min, which one is a max? You've got a 50-50 shot if you're a good guesser, but why not put some math behind it? Here, where my derivative is positive, my function is increasing. Here, where my derivative is negative, my function is decreasing. So if I have a negative derivative and a negative derivative and a positive derivative, that means this guy's a min and this guy's a max. So just by looking at each of these places where the derivative is equal to 0, at this point in my graph leading up to this 0, my derivative is negative, meaning my graph is decreasing. Here to here, my derivative is positive, that means my graph is increasing. And after that critical point, my derivative is negative, which makes this one the max and this one the min. So that's why this one has the answer of 3. So that's where we come up and just cross off 3. And there were a couple times during this conversation where I peeked at my answers and like, oh, I've already used 3, so I know the answer can't be it. And that first one happened with this next question here. Which of the following x values is g of x both decreasing and concave up? So here is my derivative. Here is my derivative. So we can factor it and find our critical points here at 2 and 6. So when I look at my second derivative, I can talk about these conversations about increasing, decreasing intervals and concave up or down and help determine that at 5, my graph is going to be concave up, and at 5, my graph is decreasing. My derivative is negative, so my original graph is decreasing. And that's again where we have those conversations between, are you talking about your original graph increasing, decreasing? Are you talking about your derivative graph increasing, decreasing? Are you talking about the slope of the tangent line of your original graph or the slope of the tangent line of your derivative graph? You have to be super careful to tease out that information. Questions on the first page? All right. So I gave you a key of the next 2 pages. So I'll give you a minute. That first page of your warm-up this morning or this afternoon, that first page has these 2 keys. So I'll give you a minute to go ahead and look at your answers compared to this. And you can ask me questions on ones you don't understand. Sound okay? On your mark is set, talk. Questions on the back page? So this one was a little bit confusing because they asked you for the absolute maximum. So your critical points weren't a part of the conversation. You just had to substitute in 0 and 2 and then see which one was higher, and that was the way we got 9 to be crossed off. So, I didn't love that question. Okay. Questions about D? Put your hand in there. Okay. So, E, at what point, or at which x value does h of x have a point of inflection? Okay. So, our critical points happen in 2 scenarios: when my derivative is equal to 0, or where I can't take the derivative. So many of our graphs have us finding where that derivative is equal to 0, but this sharp point is a good example of where I can't take the derivative. So then we have to look at what's happening to my derivative sign. My derivative value is getting smaller and smaller and smaller and smaller and smaller, 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 smaller. So as my derivative value gets smaller and smaller, it was positive, and then it starts getting smaller, 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 right? And then it transitions to where it's 0 for a while, and then it starts being negative. So if we start talking about what that looks like, my derivative was positive, and then it goes 0, and then it starts being negative, negative, negative. And then it hits a point where I can't take the derivative of it anymore, right? So then here, it automatically goes from being negative to being positive, or not being positive, from being a negative value to then increasing. So it's not positive until it hits here, but it is not getting less anymore. So then instead of it getting smaller, 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 now all of a sudden it starts getting less negative. So my derivative goes from getting smaller, smaller, smaller to starting to get bigger, 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 bigger. And that means that there's going to be a point of inflection. Sure. Any other questions? F? We good? G? You want to do G? Okay. So let's talk about G. So here is my function that I'm given, and I'm given the derivative. So there it is. How many relative extrema does it have? So when I look at this, I can see that I've got 3 critical points because there are 3 places that this derivative is potentially equal to 0. So each of these 3 are my critical points. So I can't just stop there, because now what I have to do is test and see what's happening to the derivative, to the values, the output values. So I put my critical points into my chart, and I take a look at what happens on either side of each critical point. Now I cheat when I do this. Call it cheat, call it maximizing my time, totally up to you, whatever you think is true. So what I'll do is I'll go over here and I'll enter in my values. So I'll put x to the 3rd times x minus 3 squared times x plus 1, right? So then I'll go to the table of values, and I remember my output is the sign of my derivative. So if my output is positive, that means my derivative is positive, my graph is increasing, right? If my output's negative, my derivative is negative. But I'm curious about what happens in between here, and I'm wondering if I need to like zoom in a little bit and look in between the integer values. So this button here that says table set, if I go there, I can ask my graph to go up at increments smaller than 1. So I can ask it to go up at, I don't know, 0.2. So now when I go back to my table, I'm still at -4, but see how I'm going up 0.2 at a time? So as I'm getting down to this area where -1 is, my derivative is positive from -infinity up to 1, up to -1. It's 0 at 1, but notice now there's my negative. So these areas in between -1 and 0, those were negative. So if my derivative passes through that, think about that, my derivative value goes from being negative, then it goes to being positive. That's where I'm going to have either a local min or a local max. And I can think about it in terms of a positive to a negative. This is going to be a max. If my derivative is positive and it goes to negative, okay? So then I come to 0, I'm at negative, and it goes to positive. So that one from negative to positive is going to be a minimum. So then I get to 3, and I'm going to get all the way down here to 3. I'm back to 0, but check it out. I don't go to negative. So my derivative, my output of my derivative is not negative. So that means that that was just one of those graphs that has a hitch. So it didn't change direction. So if my graph was positive and continued being positive, that's one of these kind of things. So there's no mins and maxes here. So that's why you have to draw the sign table, and that's why you have to look at how does that output of that derivative change, and what does that tell you about the graph. So that's why there's just 2 critical points. This one ends up not being a critical point because there's no sign change. All right. Any other questions? H, I, J? Are we good? Yeah? Okay. Awesome. So we decided there were too many times that you guys were mixing up the features, the characteristics, and conversations about f of x, g of x, no, f of x, f prime of x, and f double prime of x. So we came up with these next 3 pages to help you really tease out the difference between the graphs. And we're asking that you use color pencils to go ahead, or markers, to go ahead and so we're asking that you use a color pencil so that you can color on and distinguish which sides of what are behaving which way. So take a couple minutes, and we're just going to do this together 1 page at a time. So when we check out this graph, our first question is trace in green where the graph is increasing. So my graph is increasing wherever my output values are getting bigger. That's an Algebra 1 concept. We talk about it again in Algebra 2. If it's increasing and you're like, well, that was so much easier back when everything was linear, right? As you read a graph left to right, if your output values are getting bigger, then that's where you are increasing. So my justification here is my output values are increasing as I move left to right. That tells me that I'm getting bigger. When we scratch away at the calculus of it, we begin to understand that is because our rate of change is positive. Our rate of change is positive. So if we go think back to linear, you had a positive slope and it went from left to right, increasing as you went. So it wasn't that your derivative was increasing, it was that your derivative was positive. Back in Algebra 1, when you had a linear graph, that was increasing, and your slope of the tangent line was constant. It wasn't changing. It was positive. You had a positive slope. Boom, off we go. When f of x, when the slope, if f of x has a slope that's positive, that means that f prime of x is going to be positive and your output values are increasing. When you look at where I colored in red, that's where my output values are getting smaller. I have an output value here, then here, then here, then here. My graph is decreasing because my output values are getting smaller, and that is happening because my f of x, my slope of my tangent line, my f prime of x, is negative. So this first conversation of increasing and decreasing is just whether you have a positive or a negative slope. So I was watching some of you take your straight edge and draw, that's a negative slope. 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 Our positive slopes is when I'm increasing left to right. So then we start talking about, all right, let's talk about where we change from an increasing to a decreasing or vice versa. Because how do you know where to put these dots if you're looking at your extrema? Okay, well, I'm putting a dot where my graph changes from increasing to decreasing or decreasing to increasing, but that's also changing as my derivative passes through 0. So this should be as my function changes from increasing to decreasing, and where my derivative changes from positive to negative. Your function increasing, decreasing is different from your derivative being positive or negative, or vice versa. At the dot, the slope of your tangent line is 0, and your original function changes from increasing to decreasing. When we start talking about concavity, we mentioned these inflection points. Now, I went ahead and guesstimated where it is, because to me, it looks, where does the curve change paths? Because to me, if I think about continuing this parabola, right here is where I feel like it would normally keep going up like this, and instead it takes this path here. And so my slope of my tangent line that's getting bigger, 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 instead of continuing to grow, getting bigger, 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 it's still positive, but it changes from increasing to decreasing all the way to where it hits 0. So I have a positive concavity on my original graph when my derivative value starts to get bigger and bigger and bigger and bigger. And that's what's confusing. A steeper line in a negative portion of the graph, that has a slope that's way steep, way negative. So when we talk about increasing, decreasing, it's getting less steep, but that's happening because it's getting a less negative value as the slope. So my value of my slope is getting bigger and bigger and bigger and bigger. It's still getting bigger, 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 still, until I reach about here, and you're like, nope, I think it's going to get smaller and smaller and smaller. So right at these stars here is where my concavity changes from up like a cup to down like a frown. That happens because my derivative function changes from increasing to decreasing, and that happens because my second derivative changes from positive to negative. At that star, my second derivative is equal to 0. Take a minute, check in with your group mates. Tell them what you got right and what you now better understand. Go. So turn the page and spend just a minute reading. What are you looking at now? Call it out. What are you looking at? The derivative of what? Yeah. So here is your graph of the derivative, and it's the derivative of this original graph. Just upon first glance, do you buy that? Does that make sense to you? If you had to say what power this graph is generically, what would you call it? It's a quartic graph. It's the fourth power. I see 1, 2, 3, 4 solutions. I see 1, 2, 3 terms. And my end behavior matches. It's an even, right? What do you see here? Does that make sense that the derivative would be one level less? Absolutely. So get with your partner, because I know are your pages side by side like mine? Okay. Take a look at both graphs. Does your dots match up with the zeros? So it's kind of interesting when you can look at this is the derivative of this graph. Okay, let's go ahead and just consider this graph. Indicate where the derivative is positive. What do you conclude about the original function on those intervals? So for me, it's easy to talk about this. Isn't this where my derivative is positive?
Yes.
And isn't this where my derivative is negative?
Yes.
So that's worth looking at. Because when we ask you, is the derivative positive or negative, kids look at this graph and they're like, I don't know where to look. Yeah, you're looking above the x-axis for positive and below the x-axis for negative. So grab a colored pencil and make this graph clear to you. Make sure you know that this is the derivative of the original function. All right. What can you conclude about the original functions on those intervals? So wherever it's positive, whenever f prime of x is positive, what's true about f of x? It's increasing. Wherever f prime of x is negative, what do you conclude about f of x? All right, with your group mates, continue talking about and examining the derivative graph. Go. All right, consider the graph of the derivative of the original function. So I'm looking at the derivative. Here's where my derivative is positive. Here's where my derivative is negative. So when I'm talking about indicate where the derivative is positive, I did it for the derivative increasing and decreasing. Sassafras. Okay, hold on. Hold on. Wait a minute. Don't attack me. Easy. Stand down, soldiers. I'll get another color. I got lots of them. Orange. Indicate where the value of the derivative is positive. There it is. The value of the derivative is negative. There it is. And I'm okay with that, right? So this red and green is this question. I think I'm okay.
But you indicated everything that's pinning up like this.
Okay, but hold on a minute. So this positive and negative has nothing to do with these questions. Hold on. I think I'm okay. So this top part of the graph here is where my derivative is positive. This bottom part of my graph is where my derivative has a negative value. Each of these intervals is where my original function is increasing, and each of these intervals is where my original function is decreasing. We're okay with that, right? Am I okay with that? All right. So now, and that answers 5 and 6. So I kind of got ahead of myself here because it says indicate where the value of the derivative is positive and where the value of the, so wherever the value of the derivative is positive, my original function is getting bigger. If the value of my derivative is negative, my original function is getting smaller. Grace, am I still okay on 5 and 6? Because
on 5 and 6, yeah, I'm just
okay,
questioning 8
so 5 and 6 just has to do with this positive and this negative. So we're okay with that. All right. So now on 7 it says place a dot on each critical point, and this is where I messed up, and I tried to go back and fix it because the critical point of my original function is going to be where the slope of my tangent line or my derivative is equal to 0. And that's the critical point of the original function. That's going to be here, and here, and here. So where these pink stars are is not it, because those pink stars are our next question. So these critical points, right here, and here, and here, these are my critical points of my original function, because my derivative is equal to 0. Are we okay with that? Yeah? All right. So then it says, trace in green where f prime of x is increasing. So I'm okay with this, because this green shows you where f prime is increasing. So maybe it would have been better if I had chosen, I don't know, purple for this and purple for this, so we weren't confused with our green and our reds. And then if I had chosen, I don't know, magenta for this and magenta for this. Because this green and red is correct. That green and red is looking at where is my derivative value increasing. So this is where my derivative value is getting bigger and bigger and bigger and bigger. Think about when we were filling up those cups today. Is my rate of change increasing? I'm increasing at an increasing rate. That happened when my cup got smaller, right? So if I'm increasing at an increasing rate, my slope of that tangent line is positive. So while this slope is positive, and this is the wackadoo thing, this graph is concave up. Yeah. So when this derivative value is getting bigger and bigger and bigger, this is concave up. This point of inflection happens right here, where this derivative of my derivative, where my second derivative is equal to 0. So right here where my second derivative zeroes out, those pink stars are going to happen right at the same point. So when f prime, when my derivative is increasing, I'm going to be concave up like a cup. When f prime is decreasing, I'm down like a frown. And that happens because my changing value is determined by the sign of its derivative. So the derivative of the derivative is the second derivative. F prime is increasing, the output value is getting bigger. That's because its slope, the slope of my derivative is the second derivative, is positive. Where my derivative graph is decreasing, my output values are getting smaller. That's because the slope of my second derivative is negative. That's happening right here. My inflection points are going to be where my second derivative is equal to 0. So the derivative of my derivative, the slope of the tangent line of my derivative is equal to 0. So those are my inflection points, where my second derivative is equal to 0. And that's where my derivative goes from increasing to decreasing. I can add that onto this too. I could say that happens where f prime changes from increasing to decreasing, and that's where f double prime changes from positive to negative, or vice versa. I can go from negative to positive. All of the conversations of concavity are about this guy. So we can look at this guy and we can see concave up, concave down, concave up. I'm up like a cup because my derivative value is getting bigger. My derivative value is getting bigger right here. So you can see I'm up like a cup because my derivative value is getting bigger. I'm down like a frown because my derivative value is getting smaller. I'm up like a cup because my derivative value is getting bigger. Is that a little better? Where have I lost you?
I still stick with what I said. I don't know, because in the other work that we've done, it's like the way that I explained it. I'll get it later. It's fine.
So see if you can conceptualize it, because we're going to go, ready, one level deeper. Because what is this a graph of? This is the graph of my second derivative. So note, this is the second derivative of my original graph. So notice I started at a quartic. Now my derivative was a cubic. So my second derivative is going to be a quadratic. With your group, work through this one. Go. All right. So on this graph, my second derivative is positive here and negative here. My inflection points are where my second derivative is equal to 0. When my first derivative is increasing, that is where I have, where my f prime of x is increasing, that's where my original graph is concave up. The sign of the second derivative is going to tell me what's happening with my original graph. And what's interesting is you can go back to that original graph and you can look at these two together. Trying to get them both on the screen at the same time. You can look at both of these at the same time and you can say where my second derivative is positive, that is where my first derivative is increasing, and that is where I'm concave up. Everywhere that's colored green here is up like a cup here. This star and this star are at the same point. Everywhere that my second derivative has a negative value, that is where I'm concave down. And this star and this star match. All right. Here we go. At the risk of freaking you out. Here's our original graph. And we'll make this one purple. and we'll make it super thick. That's the same exact graph that we made up for this worksheet. Then we went ahead and we graphed its derivative. And just like on the board, we'll go ahead and change this graph to pink. This graph is the graph of the second derivative, and we'll make that one green. So what's super cool about this is this point here that's a extrema. This happens to be the absolute minimum, but that happens at the same time that my derivative value is 0. Same with this extrema, derivative value 0. Same with this extrema, derivative value equals 0. So when you're asked to find the minimums and maximums, wherever your first derivative is equal to 0 is a critical point, and that's where you have to test. They're not all automatically, because we can, remember we talked about the one that looks like this. So they're not all automatically. Then we can have that same conversation and we can look at where is the slope of my derivative graph equal to 0. Check it out. This is the point of inflection. Here's my second derivative graph equaling 0. And here's the point of inflection where the concavity changes. So by putting the three graphs on top of each other, we can look at how each of them affects the other. Yeah? Tie it all together. Clear away any fuzz. Say that? For the most part. Yes. So last week when we played that game, these are the game cards of the original graphs. And what I want you to do on the graphs is I want you to practice drawing the graph of the derivative. So this is the one where my slope of my tangent line is -1. I can't take the slope at a sharp point. And this is where the slope of my tangent line was +1. So do you remember this one? So for an absolute value graph, graphing the derivative looks something like that. I think on your homework we had you doing the cosine graph. And you ended up graphing, so some of these were definitely from your homework. So skip to the ones that interest you most. And as you approach them, this is where my derivative graph is equal to 0. This is where my derivative graph is equal to 0. And ask yourself, is the slope of my tangent line positive or negative? Here the slope of my tangent line is positive. Here the slope of my tangent line is negative. Here the slope of my tangent line is positive. So if I'm graphing my derivative, it makes sense that my cubic becomes a quadratic. So with your group mates, pick a graph and practice sketching the derivative.